research associate in math from Bryn Mawr. He's a math historian who specializes in the work of Leonhard Euler. And given that Euler's publication, or his work is not even close to completed publication, you know, it's as much an exercise in perseverance, I guess, as everything else. So Bill is going to give us a talk tonight on using of Euler. I'll hand it over to him.
Also, for the audience, quickly,
Hi there.
just walked in.
Can I see you lunch tomorrow? Maybe?
Sure.
What time are you going to eat?
Well, no, I can wait if people are still coming.
Huh? One.
One, fine.
And are the videos ready?
Yes.
Okay. Well, then I guess I will start. So it's a pleasure to be here at Stony Brook to talk about my favorite mathematician. Everybody should know Euler. Here's what I plan to do. Break this into three parts. First, a general biography, a quick biography of Euler, so you have some dates to associate with him. Second, I'm going to do a broad survey of some of his contributions to mathematics from various areas of the subject. And then finally, I'll actually give you a proof, an Eulerian proof from the 18th century that you will understand, and I'll bet you haven't seen it before. I'll bet it. So, lots to do. This is Euler. This is the famous portrait. When you see this, you realize why he was never an international icon of fashion. Right? What a strange thing to wear when they're going to come and paint your picture, but that's what he wore. He was born in Basel, Switzerland in 1707, and was brilliant, so that at the age of 13, he's studying with Johan Bernoulli. Now, Johan Bernoulli, you probably have run into the Bernoulli name in some of your classes. He was, at that time, probably the greatest living mathematician in the world, and he was in Basel. And so this little kid, Euler, was sent off to study with the great Bernoulli. And initially he was terrified of being in the same room with Bernoulli, but it doesn't take long before Bernoulli recognizes what a special case this is. Euler graduated from the University of Basel in 1722 when he was 15. You can do the math. And when he was 20, he went off to the St. Petersburg Academy in Russia. Now, in those days in Europe, the different courts were surrounded by academies, which were meant to enhance the nation and the monarch. So there was the Royal Society in London and the Paris Academy and the Berlin Academy, and Russia wanted one. So they set up this St. Petersburg Academy, and Euler was one of the first people there. He stays there until 1741 when he goes to the Berlin Academy. So he got traded or something to another team. He stayed there until 1766 when he goes back to St. Petersburg and stays for the rest of his life. An interesting thing happens to him in 1782. He's made a foreign member of the American Academy of Arts and Sciences. Now, the United States hadn't quite finished its Revolutionary War. The peace treaty was 1783, so this was a brand new country, but they wanted to have an Academy of Arts and Sciences. And, Benjamin Franklin was in it, and Thomas Jefferson, people like that. But they wanted some foreign members, and who was the most distinguished foreign mathematician? Euler. So they wrote him a letter to Russia and said, I would like to make you a member of the American Academy of Arts and Sciences. And he wrote back and said, thank you, I'm very pleased, I will accept the membership, but I probably won't be able to make it to any meetings. He said, because he was living, in Russia, and he was old. But it's kind of neat, and they still have that letter in the U.S. and the American Academy, where lots of other people have since been inducted, but Euler joined it. The next year, alas, he died. And here's his tomb in St. Petersburg. You can go visit Leonhard Euler, as it says in its Latinized form. I like this slide because it gives you a context, a comparison, if you know American history. Over here, Ben Franklin, famous character, scientist, politician, and he lived almost exactly the same years. They were almost exact contemporaries. Two towering figures of the Enlightenment, and Franklin was not to be outdone by Euler because he's wearing a dead animal around his neck here. So the each had their fashion statements, I guess they were making. It would have been neat if they met, but they never did. But they were two pretty significant people. On the personal side, Euler married, and he and wife Katharina had 13 children. But this was the 18th century, and child mortality was rampant. And of those 13, only 5 survived to adolescence, so there would have been great sorrow in the Euler house. Euler, by all accounts, had a phenomenal memory. Apparently he could memorize anything. And where other people have to look something up in the log table, you know, it's much easier to memorize the log table and you don't have to look it up, so he could do that. And this becomes important in the 1730s when he loses vision in his right eye. His vision is gone. And what happens is the eye actually shriveled. It was the organ, the eyeball, that had some sort of infection in it, we think, and it destroyed it. And so his eye was worthless. So he gives up, right? No, he keeps going. He still has a good eye, so his output does not diminish. And in 1771, he loses vision in the other eye, the left eye. And this is a cataract. And nowadays, that's easy to fix, but not in the 18th century. And in fact, they tried surgery on him. And you don't even want to think about eye surgery in 1771. It was horrible. It was painful, and it failed. So now he's blind. He can't see. So his productivity falls off, right? Wrong! He keeps going. He now will come into a room, and he would stand there and dictate mathematics to people, furiously writing it down, that he could see in his mind's eye, and with his phenomenal memory, his productivity did not diminish, even when he went blind. And, if you don't believe me, well, there we go. In 1775, there it is. 1775, he produced 50 papers as a blind mathematician, paper a week. So this makes Euler kind of an inspirational figure in mathematics. He was someone that would not be beaten by this physical malady. And he's kind of like Beethoven, right? In music, Beethoven went deaf and still composed music. And Euler was blind and still did mathematics. Now, his math is distinguished by its quantity and its quality. He's off the charts on both of those axes. And let me mention the quantity first, and then for the quality, I'll show you some examples of what he did. But just in terms of quantity, nobody ever did more mathematics than Euler.
What about Erich?
I'm sorry?
What about Erich?
Not in pages. Euler's page count is way higher than Erich. And Euler didn't have co-authors either. Here, let me see what you think. He died in 1783. But just being dead does not stop Euler from publishing. So, over the next, 47 years, he published 159 papers. They had found these things in his desk, in his notebooks. Some of them were in press. Then he had a little hiatus, but he had a great year in 1844 with 61 new papers published, and in 1849, 8 more. So what is it? That's a lot of papers, right? 228 papers while dead. No other dead mathematician has ever or will ever publish 228 papers, but Euler did that. It's just unbelievable how much stuff he did. In 1910, somebody named Gustav Enneström decided he would catalog all of Euler's works, count them all up, write little summaries of them, and put this out. He found 866 books and papers that Euler had done in his life. And in that regard, Erich might have a higher number than that. But Euler's papers, a paper might be 100 pages. That counts as one paper. A book might be, his calculus books were 1,500 pages long. That was a calculus. So in terms of pages, he's way off the charts. The catalog that Enneström wrote, giving a description of each of Euler's results, the catalog was 388 pages long. Not the works, just the catalog. So the next year, the Swiss Academy of Sciences decided they would republish all of Euler's works in a nice organized series they called the Opera Omnia. And in 1911, the first volume came out. And these volumes are big. Think of an encyclopedia. They're not little books. They're giant tomes. So a volume came out, and next year a volume came out. A few years later, a volume came out. They're still coming. They're not done. They've been at this for well over a century, and they're still not done. At the last count, there were 75, I think that, this slide's old, might be 77 volumes of Euler's collected works. 25,000 pages from one person. You know, now, if your lifetime productivity was 250 pages of new math, that would be pretty darn good for a lifetime. Multiply it by 10, 2,500 pages. Multiply it by 10 again, and that's what I learned. And it's just amazing. So that was the quantity. Now, the quality. All right, so let me show you some of the things he did in his career. One of them was, in his great work, the Introductio in Analysis Infinitorum of 1748, he said that the proper focus of analytic geometry and trig and calculus was not the curve, which is what people had been studying prior to this, curved lines, geometrical things. He said, no, that's not it. What you want to study is the function. And he made functions central to analysis. And if you study analysis, you'd study functions, right? And why? Because prior to that, curves were the object of study. And then he said, all right, I've got to give you the functions you need in the toolkit. So he gives you the polynomial functions. He introduces the logarithmic functions, exponential, trig functions, inverse trig functions. They're all in this great work of Euler's. And there's still the functions that are in your toolkit. You know, the ones that you need to do calculus are these. This book has been called the greatest math textbook of modern times in terms of what it did to mathematics, his great introduction. So he gave us functions, so that's pretty good. He gave us the number e. And here's where it showed up. This is his birth. This was 1748. He said, let us place, for the sake of brevity, this number, for the sake of brevity, we will replace this number, 271828, etc., by that letter, e. Let's use that, e. Which, he says, therefore denotes the base of the natural or hyperbolic logarithm. So he knew what it was, the base of the natural log, e. And he says, if you want to calculate it at home, there's how you do it. 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3. And if you know the Taylor series for e to the x, and you put in 1, of course, that's it. And it converges very fast. And it converges, and that's how he got this very accurate number. Although he loved this kind of stuff. He could multiply 10-digit numbers in his head. You know, so doing log decimals was kind of fun for him. So it's a sideline little exercise. Yeah?
Did you write everything in Latin?
Well, many of his papers were in Latin, but not all of them. This is weird. If he was in Russia, he wrote in Latin. If he was in Berlin, Germany, he wrote in French. Because at the academy in Berlin, they insisted that everyone speak French, not German. Frederick the Great, the Prussian leader, hated Germans, and he loved the French. So if you see an Euler paper and it's written in French, you know it's coming from Berlin, and if it's written in Latin, it's coming from Russia. But of course, in those days, all scholars in Europe knew Latin, so this was the common language that everybody used. It makes it difficult to read this stuff unless you know Latin and French and all this. Okay, he gave us the Euler polyhedral formula. V plus F equals E plus 2. I don't know if you've seen this in your courses, but this is about polyhedra, which are three-dimensional bodies whose faces are polygons. And V is the number of vertices, number of corners, and F is the number of faces, and E is the number of edges on one of these things. And what Euler says is V plus F equals E plus 2. Now for my cube there, that's a cube, is a perfectly good polyhedron. What's V? How many vertices? 8, right? 4 on the top, 4 on the bottom. How many faces? 6, yeah, think of a dot, right? And how many edges? Well, if you count them, you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 8 plus 6 is 12 plus 2. So it works for a cube. Easy. But what Euler shows is it works for a wide array of other polyhedra, like prisms and pyramids and icosahedra, like this, and lots of other things. And this general property is quite significant to this day, the Euler polyhedral formula. Now, we think highly of this, but back in the day, Euler said, I find it surprising that these general results in solid geometry have not previously been noticed by anyone, so far as I am aware. You know, he said, what's the big deal? This is easy. V plus F equals E plus 2. Why didn't somebody else do this? But nobody else was Euler, I guess, because he's the one that did it. Here's one. Maybe you've seen this one, the Basel problem. It's 1734, and there is a challenge afoot in Europe. Jakob Bernoulli, who was the brother of Johan, and Johan had been Euler's mentor, Jakob challenged the mathematical community to find the exact sum of that infinite series. 1 plus a 4 plus a 9 plus a 16, the sum of the reciprocals of the squares. And this was the big unsolved problem. Nobody could do it. Bernoulli couldn't do it. Leibniz couldn't do it. Newton couldn't do it. Yeah.
So was this like a typical thing to challenge?
Yes, there was a lot of challenges that went on back in the day. And sometimes you wouldn't issue the challenge until you did it yourself, and then you'd issue the challenge, and then when nobody else could do it, you'd say, see how smart I am. But in this one, Jakob couldn't do it either. He did do this, though. To his credit, he showed this converge in our language to something less than 2. He did a comparison test, essentially, and a very early comparison test. I'll talk about this tomorrow, speaking about Euler at the colloquium. But anyway, but he knew it converged to something, but he wanted to know exactly what, and he couldn't figure it out. And Euler's the one that does it. And do you know the answer? Have you seen this? Pi squared over 6. Yeah, what a weird answer. This is strange result. Looks like it can't be right, but it is, of course. And when Euler publishes this, he becomes famous. This is called the result that made him famous. He was still pretty young. And after this, everyone in Europe knew there's this superstar. At this time, he was in St. Petersburg. It would, you know, if he was alive today and this were out there, it would have been on the front page of the New York Times, or you know, somebody at Clay Institute would have given him $1 million or something for this. It would be like the Riemann hypothesis of its day. But anyway, that's something he did. Hey, geometry. You know, he worked in geometry. Now you think, wait, how much geometry could be left? You know, the Greeks did geometry thousands of years before. Surely, all the geometry was done. No, 4 big fat volumes of Euler's collected works are geometry. He went back to the sort of old subject and found new things. And let me just show you one that's pretty amazing. One of John's favorites. Suppose you take any triangle. Any triangle. Doesn't have to be equilateral or, you know, isosceles, but it could be anything. And you find the point where the 3 altitudes meet. You know, the altitude is what it goes from each vertex perpendicular to the opposite side. And the 3 altitudes go through a point called the orthocenter. The 3 medians meet in a point. Now, a median, remember this, it goes from each vertex to the middle of the opposite side. And those meet in a point called the centroid. And then you take the perpendicular bisectors, which you take each side bisected, put up the perpendicular. Those meet in a point, which is the center of the circumscribed circle, and it's called the circumcenter. Okay, so these points come with any triangle. The Greeks knew about these points. That's not new. But let me show you a picture. So here's a triangle. So let's do the intersection of the altitudes to find the orthocenter. So each one we go perpendicular, 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 and there is the orthocenter. Or perpendicular to the altitudes. Okay. Now we'll do the intersection of the medians. So they go from each vertex to the middle of the opposite side, and they all meet in the center, right? And then we'll do the intersection of the perpendicular bisectors. So you take each side, bisect, and put up the perpendicular, and there's the circumcenter. And what did Euler see that no one had ever seen about these 3 points? They line up. They always line up. For any triangle, these are going to form a line, which we now call the Euler line, because he's the one that discovered it and proved that these have to be aligned. And he proved something more, that the distance between the centroid and the circumcenter is always exactly half the distance between the centroid and the orthocenter. That line segment is always split in the ratio 2 to 1, no matter what triangle you start with. So there was still some geometry to be done in the world, and Euler did it. Okay. Here's a famous paper of his, a solution pertaining to a problem of the geometry of position, geometriam situs, the geometry of position. This was the bridges of Königsberg. And you probably have run across this somewhere or other in your life. This is a map of Königsberg. The river Pregel, I guess, comes in, it goes around this island, and there were these bridges. And the story you have to tell, if you're telling this, is that supposedly in Königsberg, the burghers wanted to take a stroll on Sundays, and they would go out here and they'd walk around, go over the bridges, look at the park and all this, and try to do this so that they crossed each bridge once and only once. And they couldn't. Every time they tried to, they either missed a bridge or they came back across a bridge they'd already crossed. So they were, confused. So they asked the mayor of Königsberg, can this be done? And he said, how would I know? I'm the mayor of Königsberg. What are you asking me for? Ask that guy down, ask Euler. So they write a letter to Euler, and Euler analyzes it and shows that, in fact, it can't be done. Not for this configuration. That's impossible. But for that configuration, it's possible. And he explains why, and he gives a proof. And it turns out to be the origins of what we now call graph theory. The theory of graphs with vertices and nodes and edges, and it's a vast, vast subject today. But it's often, its origins trace back to that. We're impressed. Euler wasn't so impressed. He said, this solution bears little relationship to mathematics, and I do not understand why to expect a mathematician to produce it rather than anyone else, for the solution is based on logic alone. So he said, this isn't even math. Math has to have cosines in it, or something like that, derivatives. And this is just reasoning. It's like a combinatoric argument. So, he said that the mayor probably should have been able to do this. But, not really. And in fact, if Euler were to come back today and see what happened to graph theory, he would certainly recognize mathematics in action. All right, one of the things he did that was really good was number theory. He's among the 5 greatest number theorists ever, probably. Number theory, the study of the whole numbers. 1, 2, 3, 4, 5. Maybe, have you had a class in this? Maybe they do number theory. Anybody's seen this? You got primes and composites and all that stuff. It sounds like it should be pretty easy. Whole numbers, 1, 2, 3. And what's so hard about that? Irrational numbers. Now those are hard, but actually number theory is really hard. Euler did 4 fat volumes of number theory, and let me just pick out one thing he did, which I find kind of amazing. This definition has been kicking around. M and N are called amicable numbers, which means friendly, if each is the sum of the proper whole number divisors of the other. So that's the definition of amicable numbers. Now, an example is in order, and here's the example, you'll see. 220 and 284 are amicable numbers. Here's what we mean by that. What you want to do is look at all the proper divisors of 220, by which I mean whole numbers that divide evenly into 220, but proper means not 220. You don't count that. It's got to be small. So there they are. The numbers that divide into 220 exactly are 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, 110. Add them up, 284. Now you take the proper divisors of 284, all the numbers that divide evenly into 284. There they are, 1, 2, 4, 71, 142. We're not counting 284 because it's proper. Add those up, 220. Each of these is the sum of the proper divisors of the other. It's totally useless. This has no value in terms of, making the refrigerator work or anything. But this is what number theorists love, these kind of strange, weird properties of the whole numbers. So at this point, I always tell a story, which is a true story. I had a friend, he was a math guy. He was getting married, and he gave his wife to be a bracelet with the number 284 on it, and he has one he wears with the number 220 on it to show their eternal friendship or amicability. It's very sweet, right? Very sweet. Nerdy, right? Yes, but sweet. So if any of you are thinking about finding a life partner, I'll just toss that out as a suggestion. You can wear your bracelets. Okay, now, here comes the brief history of amicable numbers. The Greeks knew that pair. Way back, they had discovered that 220 and 284 had this strange reciprocity. Each was the sum of the proper divisors of the other. And they wanted to find more, and they couldn't. They could find no others. nobody finds anymore until the 9th century, when the Islamic scholar Tabit ibn Qurra discovers a rule that yields 2 more pairs of amicable numbers. But apparently this rule does not make it back to Europe, in the sense that European mathematicians weren't aware of this. So they think there's just this one pair. In 1636, Fermat's last theorem fame, finds another pair, this two. 17,296, 18,416. If you take all the proper divisors of 17,296 and add them up, you get 18,416 and vice versa. So that was a pair. But that was one of Tabit's numbers. Tabit had already discovered that pair, but Fermat didn't know it. So Fermat was patting himself on the back, maybe improperly, but he did it independently. Okay, so now Fermat has found a number. Now in France, in the 17th century, there was a terrible mathematical rivalry. Fermat and Descartes, they hated each other. And Fermat just found an amicable pair. So now Descartes has to find an amicable pair to prove his word. So he goes to work, and 2 years later he finds that pair. 9,363,584 and 9,437,056. So there, he says, you know, Fermat, I can do it too. Guess what? That's the other one of Tabit's number. These are the easy ones. This is the low-hanging fruit of amicable numbers. And what Tabit had discovered was a rule that would have yielded those if Fermat and Descartes had known about Tabit's work. Hey, if my friend really loved his wife, he'd have put that number on the bracelet right under. That would really show you. 8 digits of love. 7 digits of love. Okay. Anyway, that's where the situation stood in 1638. And that's where it stood when Euler came along. No one in the next century found any more. And then in 1750, Euler looked at this problem and wrote a paper. And I'm showing it to you because, well, this is here it is, and this is Latin again. But I like the title, De Numeris Amicabilibus, on amicable numbers. But let's me say the word amicabilibus, which is a really great word. I would recommend it to you. If you're ever feeling down, just say amicabilibus. You will feel very happy. This is the paper. Here's the 284 and the 220. He starts off with that example and then goes on. So what's significant about this paper? In this paper, he finds 58 more pairs. In 2,000 years, mathematicians had found 3 pairs. In one paper, Euler finds 58 more. It's what Euler would do. He saw something that nobody else had seen. He had a formula that would just spit them out. Out would come Fermat's number, out would come Descartes' number, but out would come so many others. So, you know, you look at this and it's just mind-boggling. All you can say is amicabilibus, right? All right. So he did that. Okay. Hey, a couple more things before I get to my proof. He worked in applied math. He did, in fact, half of his volumes of his collected works are applications. You know, physics, mechanics, acoustics. He designed a pump. This is his little picture from one of his books where he's showing how to pump water very efficiently. So he could do that stuff too. And then there's this. These little circles intersecting and all, right? Everybody knows these as Venn diagrams. Right? We all have seen Venn diagrams. No. Venn was in the 19th century. I took this out of Euler's work in the 18th century. Euler was drawing the little diagrams and the little intersections to explain logical principles, so we should call this an Euler diagram if we were to be honest. However, if we were to do that, Venn is gone. What else did Venn ever do? He didn't stuff. So if we did this, Euler would get a little more fame and Venn would be obscure, and so that's not fair. So we'll still call them Venn diagrams. Euler doesn't need the publicity, Venn does. Okay, and then 2 other things, and then I promise I'll get to my proof. Here was a challenge given to Euler near the end of his life. Find 4 whole numbers, the sum of any 2 of which is a perfect square. Now this is easy. I will give you an example. Here come 4 numbers. 8, 8, 8, and 8. And if you add any 2 of them, you get a perfect square. Okay, that's not the problem. There we go. It's different. That can't be the same. Now it is not easy. And if you just try to do this by the seat of your pants, you know, just trial and error, you know, you think of a number, 1. find the number to add to it to make a perfect square. Well, how about 3? So there you go. 1. Now you got to have something to add to 3 to be a perfect square. 6. 6 and 3 is 9. But what happens when you do that? The 6 and the 1 don't work anymore. Oh, you say, okay, I'll go back and change this to a 10. So now 10 and 6 is 16, which is a perfect square, but then the 10 and the 3 don't work. So it's like you're trying to juggle and you can't get all the balls in the air. And that's just 3 numbers, and you needed 4. So if you try this, just willy-nilly, it will not work, I promise you. You need a system, a method. So Euler thinks about it, or puts it through a system, and he comes up with these 4 numbers. 1, 2, 3, 4. Those 4 numbers, any 2 of them add together, and you get a perfect square. But this is done centuries before there were computers or calculators or anything. And you just look at this and you say, how in the world did somebody in the 18th century come up with those 4 numbers? And the answer is simple. He was real smart. He had an idea. This is my cartoon. I'll show it one more time. So there it is, his cartoon. Euler was brilliant. But that's not what we're talking about tonight. So that was just a morsel. And then one last morsel. Back in high school, you factor polynomials, right? You spend gobs of time factoring things. X squared minus 1, the quadratic breaks into 2 linears. And x to the 4th minus 1 can break into x squared plus 1, x squared minus 1, and you can further factor the x squared minus 1. Although the x squared plus 1 is irreducible if you're just talking about real numbers, which they were at the time. So a conjecture was floating around in Europe that said any real polynomial, no matter its degree, can be factored, at least theoretically, into 1st and 2nd degree factors, like this, linear and quadratic. You can break them all down to that. And if you've seen the fundamental theorem of algebra, where it's recast in terms of complex numbers, and you can further factor this, and then the statement is that any nth degree polynomial can be broken into n linear pieces. But they weren't talking about complex polynomials then. But so they thought you could, but the question was, can you break any polynomial into 1st and 2nd degree factors? Nobody knew, nobody could prove it. But along comes Nicholas Bernoulli, yet another of these Bernoullis, and he said, you can't do it. You cannot factor any polynomial into 1st and 2nd degree pieces, and I, Nicholas Bernoulli, have a counterexample. And he sends that to Euler. X to the 4th minus 4x cubed plus 2x squared plus 4x plus 4. 4th degree, he says you cannot break it into 2 quadratics or linear. It's irreducible. You can't factor it. Well, Nicholas Bernoulli couldn't factor it, but that's not the same as saying it can't be done. Euler says, let me see here, can I factor this? Yes, into 2 quadratics. This one and that one. Now, 2 questions. Is this right? It doesn't look like it. It looks to me this is nuts because there's square roots within square roots here. Are you telling me this quadratic times this quadratic turns into something as simple as that coordinate up on the top? But if you want to spend half an hour doing this or something, multiply them back and it will. It works. This is right. So that's correct. And Bernoulli's counterexample wasn't a counterexample at all. But then the other question is, how in the world did he do this? How does somebody factor and get those factors? This is final proof that Euler was a space alien. But in fact, it wasn't. He tells you how he does it. It's brilliant. When you're done reading, you say, "Well, I could have done that too." Just like the mayor of Kingsburg should have figured out the bridges, but no, you wouldn't have figured it out on your own. Okay, so now finally, I'm going to get to my theorem, and my theorem is quite a significant one. Euler's identity from 1748. This: e to the I x equals cosine x plus I sine x. And before I proceed, how many have seen this at some point in their career? Okay, so, and if you've seen it proved, almost certainly it was done with series. Right, you do the series for cosine, the series for sine, the series for e, and you put it together, and that's probably how it was done. And Euler did that. That's one of the ways he did it. But he liked to return, to do a problem again, do a theorem, and get a different proof. That's how you fill up 75 volumes. You just keep doing things over and over again. So I'm going to show you a different proof that I thought very clever. Here's how he's stated it. This is from his original work. Notice he is using the e, but he hadn't yet adopted the I. So he was still writing square root of -1 here, and here. And then, this is curious, he doesn't want to write out the whole function, so he writes COS period, cos period, because it's an abbreviation for cosinus. And SIN period is an abbreviation for sinus. So he actually felt compelled to put in the periods. We adopted his notation, but we took out the periods. So we just write COS and SIN. That's good enough. Okay, so now, how in the world do you prove this strange result? Well, he's going to prove it with integral calculus. This is going to become an integral somehow. And that's what's sort of surprising, because that's not how people tend to see this. So we're going to prove this theorem, as he did. And he begins, well, I tell you what, he doesn't actually let I equal the square root of minus 1. I'm going to let I be the square root of minus 1. So it's about that notational convention. And he integrates this. He says, this is the trick. Start with the integral of dz over the square root of 1 plus z squared. Now, the calculus students here at Stony Brook can do this, I guess, if you give this to them. And if they remember trig substitution, everybody's favorite trick, you can do this with trigonometric substitution. Or you can punch it in on Mathematica. Right out. And I don't know which of those Euler used, but anyway, this is the antiderivative. Log of z plus the square root of 1 plus z squared. And if you don't remember how to do trig substitution, you can always differentiate backwards and just see it works. So this is where he's going to start. See, wait a minute. How about the plus c? This is an indefinite integral, plus c. Euler didn't put plus c. He never put plus c. If you ever lost a point from one of your professors for forgetting the plus c, take that paper back and say, Euler didn't put in the plus c. I want my point back. But he never put that in. He knew it was there, but why bother? Okay, anyway, so this is how he's starting to prove this. I don't know about you, but I don't see any connection or whatever between these. He says, all right, here's what I'm going to do now. I'm going to do a substitution. I'm going to let z be iy, where I is the square root of minus 1. Then dz, he says, will be I dy. The I comes out. The differential of z will be I times the differential of 1. And he's going to make that substitution in a minute. But hold on. Someone could say, wait a minute. I believe that if z is 5y, then dz is 5 dy. The constant 5 comes out of the differential. But this is a complex number. This is not even a real number. Are you sure it comes out of the differential? Can you pull out i's? And Euler responded to that kind of criticism with this statement. He says, if you deny me the validity of pulling out complex constants, you will shatter the foundation of all analysis, which consists principally in the generality of the rules and operations which are deemed true, whatever the nature which one supposes, for the quantities to which they are applied. So if you say you can pull a real constant out of a differential, you can pull a complex constant out of a differential, and a hyper-real constant out of a differential, and any other kind of constant, otherwise you will shatter the foundation of all analysis. So yeah, he said you can do this. So there, so dz is I. Okay, now, stick the values in. And what happens here is where the dz is, we got I dy, square root of 1 plus iy squared, because that's what z is, and over here log of iy plus 1 plus iy squared. Now, what's iy squared? It'll be what I squared y squared, but what's I squared? Minus 1, yeah. So from this, we can get, instead of the square root of 1 plus iy squared, it's the square root of 1 minus y squared, because I squared is minus 1. Likewise here, and I guess I turn these around, so I put the square root first, so you get 1 minus y squared. And he pulls out that I outside the integral. Can you take imaginary numbers outside of integrals? Yes, otherwise you will shatter the foundations of all analysis. So he says, do it, do it. Okay, so he had never studied complex analysis, but he just did it. Okay, so now there's the I outside. Okay, now what? Time for another substitution. There's more letters still. We haven't used up all the letters. So how about, let's let y be sine x. Okay, and dy is cosine x dx, and we substitute again. So now we have I, up here dy is cosine x dx, square root of 1 minus y squared, 1 minus sine squared, log of the square root of 1 minus sine squared, plus I sine x. Now, what's 1 minus sine squared? Cosine squared. And what's the square root of that?
Cosine.
Cosine. Yeah, and so the square root of 1 minus sine squared becomes cosine in both spots. So take it up here. Cancel the cosines. And he's got I times the integral of dx on the left, and the log of cosine x plus I sine x. But the integral of dx, anybody can do that one, that's x. So ix is the log of cosine x plus I sine x. And you're saying, he's not going to do what I think he's going to do. Yes, he is. He's going to exponentiate both sides. And on the left, you get e to the ix. And what's e to the log of cosine x plus I sine x? It's just cosine x plus I sine x. And that is how he derived Euler's identity via integral calculus. And I think that's quite amazing. I mean, it gets a lot. Actually, it gets more than a lot. It gets an amicabilis, I think. But you know, this is how he would do things. Now, you could argue there's all sorts of questions that he just sort of swept under the rug, like pulling out these constants and on, you know. But for the time, this was as rigorous as it got, and it was brilliant. That was brilliant. Hey, from this equation, the Euler identity, if you're teaching this, you have to go where I'm about to go. You have to. It's in the contract. Mathematicians have to. You let x equal pi, and you get e to the I pi is cosine pi plus I sine pi. But cosine pi is -1, and sine pi is 0. And so e to the I pi is -1, follows immediately from this. And then what they usually do is put the -1 over on the other side, and so you get e to the I pi plus 1 is 0. That follows instantly from Euler's identity. And this has been called the most beautiful formula in mathematics. They actually did a poll of mathematicians. This was some years ago. In fact, it was so long ago that if you wanted to participate in the poll, you had to send in a postcard. You couldn't do it online because there weren't computers. But when people did this, what's the most beautiful result? Pythagorean theorem, this or that. This one, e to the I pi plus 1 equals 0. That was regarded as the greatest formula of all. Because it connects the 5 greatest constants of all. I mean, if you were going to have a party and wanted to invite the greatest constants, you'd invite 0 and 1, additive and multiplicative identities. You'd invite e if you wanted to do calculus, pi if you wanted to do geometry, I if you want entry into the realm of complex numbers, e, I, pi, 0, 1, the dream team of numbers, right there. And they're all connected by this formula. There's no reason they should be. I mean, why should the 5 greatest numbers all be connected like this? And it's just brilliant that it just falls right out of Euler's identity. So it becomes the #1 greatest formula of all time. It's so beautiful that someone wrote a poem about it. And even though it is almost 8 o'clock, I'm going to recite this to you. So here comes the poem. E to the I pi plus 1 equals 0 made the mathematician Euler a hero. From the real to complex, with our brains in great flex, he led us with zest, but no fear. Oh. So, okay, it ain't Shakespeare, but that's okay, one last thing. Here's something else Euler does. He says, I want to figure out what is the square root of -1 to the power square root of -1. That doesn't even make sense. What's a complex imaginary number to an imaginary power? Or we can write it I to the I. And he's trying to figure out what this is. Well, he does. Because he goes back to Euler's identity. E to the I x equals cosine x plus I sine x. This time he lets x be pi over 2. So e to the I pi over 2 is cosine pi over 2 plus I sine pi over 2. Cosine pi over 2 is 0. Sine pi over 2 is 1. And so this comes out to be I. So e to the I pi over 2 turns out to be I. Now, if you've done complex analysis or anything, that's obvious, but it wasn't obvious back then. This is kind of amazing in and of itself, that I could be written that way. But now what he says is, if I wanted I to the I, leave the exponent I alone, but this I on the base can be written as e to the I pi over 2. So I to the I is e to the I pi over 2 to the I. And now, he says, you know the rules, you multiply the exponents. If you have a cubed squared, you multiply to get into the 6. But you say, wait a minute, Euler, these are not integers up here. These are complex numbers, and you know what he would say to that. I won't repeat it. We don't want to shatter the foundations of all of that. That's how exponents work. He multiplies them. I squared is minus 1, so you get e to the minus pi over 2. And so out of this emerges this amazing fact that I to the I, the square root of minus 1 to the power square root of minus 1, is that e to the minus pi over 2, which is 1 over square root of e to the pi. It's a real number. The square root of minus 1 to the square root of minus 1 is a real number. You punch it in on the calculator. And nobody had ever seen anything like that before. It's really quite miraculous. And there's a story that the mathematician Benjamin Peirce had been teaching this problem at Harvard. This is Peirce. I've spent my whole life trying to look like this guy. Anyway, Peirce taught this expression that showed that I to the I was 1 over the square root of e to the pi. And then he supposedly told his class he had no idea what this equation means. But we may be sure it means something very important. It can't be that weird unless it's very important. So, okay, so this is Euler. This is what he's given us. Let me leave you with a quotation. I don't have a source, but it's a good one, and I think it's apt here. Somebody said, "The talent is doing easily what others find difficult." That's what talent is. Genius is doing easily what others find impossible. And if that is our definition of genius, then Euler satisfies it. So I will leave with a shout out, way to go, Uncle Leonhard. Thank you.
Any questions for Bill? Did he pick the letter E himself?
Did he?
Did he pick the letter E for himself?
Oh yeah, that's one of the questions. Did he choose E because his name was Euler? Actually, probably not. He was a very modest person. He was a very nice person. Some of these great mathematicians, if you get to know them as people, they were not necessarily very nice. Gauss was kind of icy, and Newton was absolutely awful. But Euler was a nice guy, and you just don't think he would try to do self-aggrandizement and use the letter of his last name. It was for exponential. He chose E for exponential. There's this story about him that when he went to St. Petersburg, where all the scholars were from somewhere else, they weren't Russian, they were imported from France and Germany and Switzerland, they didn't learn Russian. Because Russian was the language of the peasants, the people that cleaned your house. He learned Russian because he wanted to talk to the grocer and the mill, the letter carrier, and people in the street. So he was a nice guy. This is good. But the E is for exponential. Yeah.
What any of his children is something that we know of?
Yeah, his children were not, of course, as good as him.
Nobody.
One of his sons was named Johan Albrecht Euler, and he became a mathematician.
Brave man.
Yes, brave man. Now, he collaborated with his father while his father was still alive, and there's this story that there was something called the Paris Prize. There'd be a challenge. You were asking about challenges. They'd put out a challenge, and people had a year to submit a solution, and whoever got the best one would win a lot of money. It was thousands and thousands of francs, but in modern dollars, it would be like $1 million. And Euler won it 13 times or something in his life, so he made a lot of money with that. But the one year, his son submitted a solution, Johan Albrecht, and it won. Great, so Johan got the Paris Prize. But his dad was still alive. After that, when his dad died and Johan Albrecht submitted a solution, never won again. So some people think maybe he got a little help on his homework, from dad. But otherwise, I don't think any of the other children went into the sciences, and beyond that generation, I don't know at all what happened. It's not like the Bernoullis. All these Bernoullis and their sons and cousins and nephews were all scientists, or the Bachs were musicians, race car drivers. Kids become race car drivers, But Euler's family had sort of petered out. It did not continue down the line.
Any other questions?
Have your autograph?
All right,
Okay, let's thank you again.
Thank you again.